Hey scholars, it's good to be back with you, and this is the second in a series of 2 videos on reviewing algebra. Now I get a lot of questions about algebra, and I gather that for a lot of us, our last algebra class was a long time ago, and maybe some of our memories aren't as fresh as they could be, so hopefully this helps. In the first video I talked a little bit about some of the basic ideas in algebra. If you want to go back and review those, that might not be a bad idea. In this one I want to go over some of the more advanced ideas in algebra. And the first one is exponents, the next one's roots, and the final one is what to do when you have more than one variable. How do you think about that? How do you draw pictures of that? So let's start with exponents. Exponents are pretty simple in concept. If we have a variable, say x, and we want to multiply it by itself a couple of times, there, like that. Now this might look kind of funny. A lot of times when you see multiplication, you see it like this. So 5 times 3 is 15. And that right there, that little x means multiplication. That's one of the symbols we use, and it's been around for a long time. The problem is that times sign and that x look almost exactly alike. And it's easy to get confused between the two of them. So in order to avoid that, a lot of times mathematicians and engineers will use a dot there. It's actually a specific case of something called a dot product for multiplying vectors. But a dot is routinely used to show multiplication. Well, this is correct, but it's kind of cumbersome. And in mathematics, the aesthetic is we try to write as much as we can, as compactly as we can. And so a more compact way to write this is just to put that exponent up there. And this is just notational. This and this mean exactly the same thing. Well, what's the inverse of this? If I have x to the third power, how do I extract x out of that? Well, let's say let's see, x cubed, let's say that's 8, right? Well, this turns out to be 2 times 2 times 2, so this is what's called a perfect cube. How would you solve that? Well, notationally, the way you do that is you take that x cubed and you take it to the 1/3 power. Now, just because the notation originally came from multiplying x by x by x and raising that to the 3rd power, mathematics is general. Mathematics generally doesn't care what kind of numbers you use when you're performing some kind of function. So even though it came from an idea where that has to be an integer, in its most general case it doesn't have to be an integer. The exponent can be any number you want, and it can easily be a third. So when you have a number with an exponent raised to an exponent, what you do is you multiply those two exponents together. So what you get now is x to the 1st power, which is just x, and 8 to the 1/3 power. This is another way to write what's called a cube root. If that 3 wasn't there, it would be a square root. If that 3 is there, it's called a cube root. Okay, and that's 2, because 2 times 2 times 2 is 8. So that's how you deal with exponents. One other thing is that another notational thing, what do you do if you have 1 over x times x? Well, that's 1 over x squared. And notationally, one of the ways we can show that, this is certainly correct, this is certainly correct. But again, we want to write things as compactly as we can. We'll write that x to the -2 power. X to the -2 indicates that the exponent is in the denominator here. So these all mean the same things. So we got exponents pretty much taken care of. All right, what about roots? What's a root mean? Well, mathematicians, when they see an operation enough times or some mathematical entity enough times, they give it a name. So when we have operations that have names, that just means they're common enough that they were worth naming. They don't necessarily have any intrinsic meaning of their own. They're just common enough we needed a way to talk about them. So long time ago, hundreds of years certainly, people noticed that if you plotted a function, there were places where that function would go through the x-axis. So up here the function is positive, and down here it's negative. Well, right there and there, f of x equals 0. Well, for physical reasons, those tend to be pretty important points. in the case of, say, ballistics, where something's flying through the air, where f of x equals 0, that's usually where it hits the ground. That's where the altitude is 0. There are many, many cases in mathematics where finding where the function crosses the x-axis is a very useful thing to do. And it's so important it has a name. And so finding these points here, this is either called a root or a 0. I'll get out of your way here. That's either called a root or a 0. Now, why does it have two names? Well, most likely because mathematics was developed over thousands of years by God knows how many people, and people in different places saw the same functions being used or same operations being used. They didn't always come up with the same name for it. So this is called a root or a 0. If you're on your scientific calculator, you'll look for the 0 function. If you're working in MATLAB, you'll look for a function called f0. If you're working in Mathcad or some of the others, it's called a root. They mean the same thing. They're just different names for the same thing. So how do you find one? Well, in the case of a parabola, it's pretty simple. There's actually a quadratic equation. Parabola and a quadratic curve are the same thing. So if y is ax squared plus bx plus c, okay, and this is just a general case of a second order polynomial, there is a quadratic equation. Because this is second order, okay, let's say this could be a parabola here because it has the right shape. A second order equation will cross this axis twice, or at most twice. It crosses it twice if the two roots are real. If the two roots are complex, it won't appear to cross this axis. It does in the real imaginary plane, but along this axis, a complex root does not show up. So in this case, it does though. So well, the notation here is x1, 2, because there's going to be two roots, equals negative b plus or minus the square root of b squared minus 4ac all over 2a. That's called the quadratic equation. And one of the reasons we use quadratic expressions here, or parabolas, is number one, they're pretty handy. They show up in physics a lot in other places. But also, you can just write the equations down. This comes from an operation called completing a square. The development of this is pretty straightforward. There is a cubic equation. If this has one more term that has a exponent 3, there is such a thing as a cubic equation. There's even a quadratic equation, but it's about that long and it's hardly ever used. For functions any more complicated than this, we almost always go to computers and use numerical algorithms, and I'll show you that here in a minute on my computer. So this is what roots look like. Finally, what happens if you have more than one variable? Right now, we've only got one independent variable. We've only got x. So what if I had f of x, y? So I've got two independent variables now. Now I can't plot this on just a 2D curve. Now I need a surface, a 3D curve. And so if I had x minus 1 squared plus y minus 1, whoops, let's see if I can fix that, squared x squared plus y squared plus 2. Okay, that's a ratio of two polynomials. I'm squinting because that's what I have on my screen down there. I'll show you this here in a minute on my computer. That has the independent variables x and y, and now the function is a function of two variables. How do you draw that? Well, it looks like this now. Okay, again, I'll get out of your way here in a second. Okay, so there's three axes, x, y, and z really, but with f of x, y. And they obey the right-hand rule. If you grab this and spin x into y, your thumb points up in the z direction. I'm left-handed. It's actually kind of handy because I can write x, y, and z on my fingertips and still write on my paper. But this is what it looks like. These are all perpendicular to one another. Okay? And so what I can do is I can define a range of x's and a range of y's, draw a grid like that, and every one of those grid points, I'll calculate f of x, y, and that'll be in this vertical or z direction. And we can make a surface out of that. So as soon as we're done here, I'll go to my computer and we'll show you how to do that. So what that looks like on the screen. So we've got roots more than one variable, and you can see pretty quickly we're going to need to go to a computer to do anything too much more elaborate than that. So let's do that right now. Let's go to a program called Mathcad. It's a kind of a math scratch pad, and I'll show you that on my computer. Okay, here we are in Mathcad, and all I'd like to do here is some sample calculations to illustrate some of the things we talked about on the board. So I'm going to start, let me go up here and define a function x plus 1, right? And let's plot that. Insert graph, xy plot. Now this is a very, very simple function. It's just a straight line. It looks just like that, as one would expect. And let's go ahead now and make, let's make f2 of x be f of x squared. That's what that's going to look like. Oops, not fs. How about f2? There we go. So we've got both of those there now. I'm going to blow this up a little bit. There, now we can see both of them. Both of our curves here. That's f1, the red line, and f2 is the dotted blue parabola. Well, what would the square root of f2 look like? Let's just call f3 the square root of f2. In fact, let's move these around here to keep things tidy. What I can do here is I can go up and just clean that up. There we go. Well, what would f3 look like? Right, it should be the square root of the square f3 should be f1, but it isn't exactly. See right there? That's negative and that's positive. Let's put some grid lines in here and let's explore this a little more closely. Okay, the green line, which is the square root of f squared, is positive, but f of x, x1, is negative right there. When Mathcad and when most numerical programs, most number crunching programs give you the square root, they only give you the positive, but it's actually positive and a negative. If I look at that value right there, could be, I don't know, negative 5 perhaps. Well, the square of negative 5 is negative 5 times negative 5, and that's 25. Take the square root of that. The square root is actually positive or negative 5. The software is reporting the positive number, even though the negative number is the one we started with. So this is the square root is the inverse of the square, but the square root could be positive or negative, and the software doesn't always tell you that. Now, once you get above 0, of course, now they agree. The green and the red overlay each other. All right, let's now see how to find the root of a function. I'm going to define another function, a different one this time. Okay, 2x squared plus 3x minus 2. Well, what does that look like? Let's go down here. By the way, I just hit Insert Graph. See that little @ sign right there? That's the fast key or the hotkey for this. So I just hit that. There's what it looks like. Well, yeah, I don't know if that helps very much. Let's put some grid lines on there so I can see where the roots might lie. I don't like those green lines. Let's make them gray here. There. Well, looks like right in there it might have, the curve might have gone below the x-axis. So let's zoom in a little bit. Let's look between maybe -4 and about 2 on the x-axis and see what this looks like. Oh yeah, there it is right there. So it looks like one of my roots must be about 2, and I don't know what that is, about a half, more or less. Now, I could go into the quadratic equation, and I could certainly figure out what this is, what the two roots are. In fact, let's do that. Okay, so let's see. This is a is 2, b is 3, and c is minus 2. This is how we the quadratic equation is defined. Let's give me some space there. So negative b plus square root of b squared minus 4 times a times c all over 2a, and I get a half. All right, my other possibility is, what if it's the negative square root? Okay, I'm going to, refresh the screen here, clean everything up. Right there, let's make minus, and then that's 2. So there, or minus 2. So there we are. There's the two roots according to the quadratic equation. Well, this only works for quadratic polynomials, and so it's useful, but it's limited. There's a more general way to do this, and that's the root command in Mathcad. Okay, you have to give it an initial guess. A lot of numerical algorithms require an initial guess. That's what that is. That's just a seed, basically, to go into the algorithm. Oops, let me try that again. F of x, and it needs to know what variable I'm interested in. So there it is. So there's minus or plus 0.5. That's that root right there. How am I going to find that one? Well, maybe if I give it a different starting point, it'll find the other root. Because these algorithms don't know what you want. They don't really know what the function looks like. There. Okay. Let's go ahead and give it a, I don't know, minus 4. And there it is. There's the negative root. So if you give it the right seed, it'll converge on the right answer for you, the right root, the one you're looking for. So there's how to find a root. There's what it means. A root is where the function crosses the x-axis. All right, so last thing now, what happens if I have a function of more than one variable? Let's do this. So x minus 1 squared plus y minus 1 squared divided by x squared. This is just a ratio of polynomials, and it looks interesting when you, oops, let me try that again. There we go. The reason that 2 is in the denominator is because if x is 0 and y is 0, the denominator is 0. Well, I don't ever want that, so I add the 2 to it. These two will always be either 0 or positive. So what I can do now is go insert, graph, and now I want a surface plot. I have 2 independent variables now instead of 1. So in order to plot, I need a 3-dimensional plot. 2 independent variables plus 1 dependent variable. So let's do that. All I got to do now is just put in f, and there it is. There's what it looks like. It's a little rough. We can clean this up a little bit, make it a little more easy to look at. So let's go to Appearance, turn on the color map, and hide lines. Oh, that's nice. That's better. It's still a little blocky though. Let's go in here, and instead of 20 points each way on the grid, let's make 40. There. So now we have a surface, okay? 2 independent variables, 1 dependent variable. And about the only thing I don't know right now is which one of those is x and which one of those is y. So I can go on and just turn those labels on here. And there, now I even know which one is which. Okay, so that's now a 3D plot, 2 independent variables and 1 dependent variable. This is the limit though. What if you have 3 independent variables and 1 dependent variable? Well, I don't know how to plot that. I live in 3 space. I don't live in 4 space, so I can't imagine what 4 dimensions looks like. I can go online and I can find pictures that are 3-dimensional shadows of a 4D space, but that's not that helpful. If you need to plot, you are limited to either 1 or 2 independent variables because we live in 3 space, and that's kind of how our brains work. So there you go. We've looked at exponents, roots, and how to plot functions of more than one variable. I hope this helps, and we'll talk to you next time.